All right, good evening, calculus geniuses. So I want to pick up where I left off with today's lesson with the volumes of excuse me, solids with known cross sections. And in the interest of saving some time, I did not write out this entire question in today's class. So I want to now take a look at the full question as it's usually presented to you. So it says, find the volume of the solid whose base is the region bounded by y equals square root of x equals 4, and the x-axis, and whose cross-sections are squares perpendicular to the x-axis. So we essentially did this entire problem here this morning, but I had a different equation here. It was y equals 6 minus x, I think, and it was pretty easy to figure out that we were going to go from x equals 0 to x equals 6 because that's where it was going to hit the x-axis. So yeah, but I shortcutted all of this and I didn't put all these words in, but this is the way the question is usually presented to you. Okay, so as usual, it's still good for us to draw a diagram. And I am thinking I want to move my setup here. And in fact, yeah, I'm just going to move my setup here. I'm not going to repeat all of this. I'm just going to spin it around the table because I don't like the way the shadow is. Hope this works out okay. That's interesting. It may be a little grainier, but it won't be shadowed, I think. All right, well, we'll give it a whirl. Let's see what happens. Let's see what happens here. Oh, that's interesting too. Oh, well, that's not good. Oh, we have to go here. Sorry for my adjustments here, but it's the way it is. Okay. So we are going to find the volume, and I hope this is going to be bright enough, of this region right here. So the first thing we need to do is we need to make a little sketch of our square root of x. This is certainly easier for me to see because of the lack of shadow. Hopefully it's going to be okay for you. Okay, so we're going to make our little square root of x, and we're going to go over to 4. So 1, 2, 3, 4. And that means we're going to go up 1, 2. And here we are. And so here's our region, this little curvy space right here. And we got our x equals 4 right here. And so this is the region right here that we're talking about in this space right here. And in class today, I had little squares, right? I grew little squares out of the board, or in this case, out of the paper. And so we're going to do the exact same thing. So we already decided today that in order for us to find the volume, well, we didn't decide this today, but we decided some other day, volume equals the integral of area. And so we're dealing with squares. In our case here, we're going to have volume equals the integral of the area of a square, which we already decided today was side squared. And so, in this case, the length of a side of the square is really just the height of the function here, which is the square root of x. So we'll set up our little integral here. And so the volume of this thing right here is going to be given by the integral of the side, which is the square root of x, squared dx. We're going to go from x equals 0 to x equals 4, 0 to 4. And then sorting this out should be very simple, right? Squaring the square root of x is just going to be x. And then we're going to plug in 4 and 0, so it's just going to be 4. So that's actually pretty simple. So I'm just kind of reviewing here the idea and showing you what this thing looks like in terms of I know how to make this better. In terms of what the question really looks like. Okay, I'm going to try to make one more adjustment here. right there. Oh, 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 oh. Yeah, I think this might work. All right. I gotta sit kind of sideways here, but we'll manage it. Okay, I'll have to do a little reaching as well, but we can do this. Okay, so there it is. This is much better light, and there's no shadows, and this is good. Okay. All right, so there we go. So that's the first problem. So I'm not going to keep rewriting these words over and over and over again, so I'm just going to put dot, dot, dot. So same words. Our new region is going to be y equals x squared plus x plus 1, and the lines y equals 2, x equals 2, and x equals 5. And again, we're going to make squares. So let's make our little sketch of this thing right here. So we have our region right here. I'm kind of reaching a little bit, so I may not be in as good a control of my writing as I'd like to be. 1, 2, 3, 4, 5, and the line y equals 2, 1, 2. So we're going to go across here, and x equals 2. We're going to be here, and 5. And so I'll just get at least a starting point right here. So I'm going to plug in 2 for here. So 2 squared is 4, plus 2 more is 6, plus 1 is 7. So here I am at, I don't know, I'm going to make believe that's 7 right there. And this is a parabola, so we're going to go up like that. And so what I have again is this region right in here, and I'm going to grow squares out of this region, square out of the paper towards you, and then back down to the paper, and we have our little square. So again, what we need to know is, well, what is the side of one of our squares? So the side of one of our squares is simply going to be the function here, subtract this thing right here, which is y equals 2. So that's what we're going to integrate. We're going to integrate from x equals 2 to x equals 5. We're going to integrate from 2 to 5. Volume equals. And we have this thing right here, x squared plus x plus 1. I'm just going to make some extra parentheses here, even though I don't need them. It's that thing minus this line right here, minus 2. And I put all that in parentheses, and I square it, because what we're doing here is, again, finding the area of a square, and we're integrating the area of something. We're integrating the area of a square, and so all we need to know is what the side is, and then we square the side, and we're golden. So, of course, we would do x squared plus x plus 1 minus 2, so x squared plus x minus 1, square that out, and then integrate each of the pieces, and then plug in 5, plug in 2, subtract, and bada bing, bada boom, we're done. So that's our second example, still using squares, and we just had a more complicated region to work with. Okay, let's move on to our next sitch right here. Naturally, things start to get a little bit more difficult. So here we have the region bounded by y equals x plus 1, a nice straight line. The x-axis, that's good, at x equals 5. I guess I should have said the y-axis also. Let me put in here the y-axis. So we're going to make our little region right here, and we'll talk about the semicircles, and this one won't go too bad. The other two you're not going to like very much. All right, so we're going to go to 5, so it means we need to go to 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So we got the region from here to here. And we're connecting that line right there. Wow. I'm trying to draw by looking at the screen, and it's a little delayed, and so, things are not so good. Okay, and then we have this line x equals 5. We got the y-axis. So here is our region right here. And instead of growing squares out of this, right, we have the side of the square. We're going to grow it straight out towards you, back and down. We have a nice square. In this case, we're going to have semicircles. And if I was even really well prepared, I would have created a little semicircle. And, you know, we have the little semicircle that starts to grow up and comes back down. You know, we get a little semicircle here. So we still need to represent the area of that semicircle thing. And so, again, I'm going to draw this bit right here. I'm going to say, well, if this is, if there's a semicircle right here, this is going to be the diameter of our semicircle. So let's see if we can figure out what's going to represent the area of a semicircle if we know the diameter. So we know the diameter. Well, first of all, we know the area of a circle is pi r squared. But we don't want a full circle. We only want half a circle, right? We only want the circles that are growing out of the paper, not ones growing through the bottom of the paper and coming back up. So we want half of that. So we really want 1/2 pi r squared. And the radius is really half of the diameter. So it's really going to be 1/2 pi times 1/2 d squared. So 1/2 squared is going to be 1/4 times 1/2 is 1/8 times pi times d squared. And so what I just did here is I just demonstrated how to find the representation of the area of the cross section that we're going to be using. So it says here that we're going to be using semicircles as our cross sections. So we need to go through and need to do a little geometry here, a little work, to develop our little formula for the area of a cross section based on the thing that we have, which in this case is going to be the diameter of the circle. So now we know that this is the area of the thing. The diameter is really just this distance from here to here. And what that distance really is, of course, again, as usual, is just the height of the function. So it's going to be x plus 1. So in order to do this problem here, we're going to integrate. And we're going to go from 0 to 5 of 1/8. We're going to kick these things out in a minute. 1/8 pi times, so the diameter squared. Well, the diameter is this, which is really just that. X plus 1 squared dx. So we'll kick these two guys onto the outside. I should have written v equals. So that's going to be equal to pi over 8. Slide this up just a little bit. Integral of 0 to 5 of x plus 1 squared dx. And again, as usual, we'll just, actually we could just substitute this right now because the derivative of x is 1 and we got a 1 here. But anyway, we could also just square this out, integrate each of the pieces, plug in 5, plug in 0, do the subtraction, and then multiply that whole result by pi over 8, and we'd have our answer. And again, I'm just saving some time here, not doing the integration because, you know, again, I'm totally confident that you can all integrate x squared plus 2x plus 1 and plug in 5 and 0. Totally got that. Okay, so this is semicircles being grown out of this situation right here. Okay. So a lot of times the difficult part of doing these problems is not making the sketch, is not setting up the integral, but it is figuring out what this is. And so that's going to be our struggle for the next problem. Okay. Again, I forgot to write y-axis here. Excuse me. Y-axis. So it's going to be the same region, y equals x plus 1, x-axis, x equals 5, y-axis, but this time we're gonna create equilateral triangles. So before I even start grinding into that whole region here, let's actually just draw an equilateral triangle and see if we can figure out what the area of an equilateral triangle is if we know what the base is. Incidentally, the base, of course, is going to be the same as all the other sides. Damn it. I wish that you could actually see what it is that I'm looking at here. I'm looking at the screen. It's all delayed. My screen has cracks all over it. And yeah, so it's, you know, you would think it's pretty easy, but it just isn't. Not for me anyway. So in any case, so we have an equilateral triangle here, or in theory, an equilateral triangle. And so all of the sides are the same. And so in an equilateral triangle, we can drop a altitude straight down. And so let's say we have a side and a side and a side. And since this is an equilateral triangle, we know that this is going to be 60 here. This is 60 here. That was 60 up there, but now it's actually 30 and 30, which is still, of course, 60. But so what I'm saying here is we have a 30, 60, 90 triangle with S on the hypotenuse. And then obviously right in here, we're going to have 1/2 S. And then what we need to do is sort out, well, what's this bit right here? So we can draw our little 30, 60, 90 triangle over here with our S and our 1/2 S right here. And what we don't know is the altitude. And we have a couple of different ways to do this. I think probably the easiest thing to do right now is just Pythagorean theorem, because sorting out the bits on the, oh, actually, 30, 60, 90, how would we feel about that? Yeah, let's just do Pythagorean theorem. Okay, so we just need to figure this thing out right here, and this is going to be A for altitude. So we got A squared plus 1/2 S squared. 1/2 of S squared equals S squared. So A squared equals 1/4, nope, plus 1/4 S squared equals S squared. S squared minus 1/4, S squared is 3/4 of an S squared. 3/4 S squared. And then we can take the square root of both sides, and we get A equals √3/2S. So that is the altitude of this triangle right here. It's also the altitude of this triangle. And so now that we know the altitude, which is also known as the height of the triangle, we know that the area of a triangle, area equals 1/2 base times height. Well, we know in this case that the base is S, so it's going to be 1/2 S, and the height is √3/2S, √3/2S. So that's going to be √3/4, √3/4 side squared. Okay, so this is the thing that we're going to end up integrating here. And we just need to figure out what is the side length. Well, let's go back to the problem now. So we're going to have y equals x plus 1, x-axis, x equals 5, y-axis, and equilateral triangles perpendicular to the x-axis growing out of the paper. So we can draw our little diagram here now. So it's really the same as before. 1, 2, 3, 4, 5. Hopefully I'll connect the dots better. 1, 2, 3, 4, 5, 6. We'll go over to here. Oh, it's actually kind of right there, isn't it? Right on the edge of that box. That's fine. And we're here. And try to do better this time. There we go. That was better. And we got right here. Kind of missed that a little bit, but that's all right. And so again, we have one of our little pieces right here. And so we're going to have an equilateral triangle. Here's the bottom of the triangle right here. The point of the triangle is going to come right at you, right? And so it's going to be a equilateral triangle grown right out of the paper, not through to the other side, right? Again, so here's the base. The point is coming right up to you and right back down to here. So we have an equilateral triangle. And we now know that the area of an equilateral triangle is this guy right here. So we know that the volume of this region right here with equilateral triangles growing out of it, right? Equilateral triangles growing right out of this thing is going to be volume equals the integral from 0 to 5 again, 0 to 5. And we know it's going to be √3/4. √3/4, right? Because we're integrating the area, this is the area, of side squared. but we know that the side is just going to be the distance from here down to here, and that distance is still right there, x plus 1. So it's going to be x plus 1 squared dx. And of course we'd kick this onto the outside, square that out, integrate it, plug in 5, plug in 0, multiply by root 3 over 4, and boom, we have an answer. So again, I want to emphasize that the real hard work here was getting this thing right here, and then this thing right here, right? This was the real hard work, getting to this, right? Look, here's all this work that we did so that we could write that thing right there. And then again, once you write this, it should be easy. All right, so, did I do one on the other side yet? Yeah, so I already did that. Okay, so the last one, it's going to be, again, the same region, and we're going to have isosceles right triangles with the hypotenuse on the base. So I'm going to encourage you right now to pause the video. I know you're just going to watch it, but I would encourage you right now to pause the video and try to create the area function, or the area expression that we need, so that we can integrate that area thing for an isosceles right triangle whose hypotenuse is on the base. So same diagram, right? So the hypotenuse is right here, and then coming out of here is the triangle with a right angle right here at the top, and then coming right back down to the paper, right? So hypotenuse here, right angle up here, and the two sides that are coming out of the paper are of equal length, isosceles right triangle. So where's that going to be? Right here. Okay, so in theory, you've paused, you've worked through this, and now you're going to be able to set it up. So, and you're going to check right now to see, well, how did I do? All right, so let's get our little isosceles right triangle here. Here's our base of our isosceles right triangle, and here is our right angle. I'm going to have to adjust here a little bit. There it is. So here's the right angle, and here is the two equal sides, making this 45 and 45, of course. And so we know here we have a side, or the hypotenuse, whatever, we'll call it h for hypotenuse. So we want to know, well, what is the area of this triangle right here? Well, the area of this triangle here is still going to be the same as it was just a minute ago. The area of a triangle is still 1/2 base times height. Well, but my base is called h for hypotenuse. And then we have a for the altitude. So we can still sort out the various parts of this so that we can figure out the area of this thing right here. So again, we're going to have an h right here, and right here we're going to have a 1/2 h. And if this is if this is 1/2 h, well then that's got to be 1/2 h. So we got a 1/2 h here, and we got a 1/2 h here, and something is not right. Oh, this is not h. Drug addict. Okay. All right, so this is 1/2 h right here. That's a 1/2 h right here. And in fact, we don't even need to know this. Yeah, because we have our little right triangle here, right? We got our right triangle. We got 1/2 h here, and we got 1/2 h here. So the area of this guy right here. So again, the area of a triangle, area equals 1/2 base times height. In this case, the base is h for hypotenuse, not h for height. And the height of this is, I forgot my 1/2. 1/2 base, which is this, times the height, which is 1/2 of this. No. What am I doing here? Yes. 45, yes, 1/2. Good. My brain is not working well today. 1/2 h times 1/2 h. Right, so it's 1/2 base times the height, which is 1/2 h. Right? 1/2 base times height. The base is the h, the height is 1/2 h. So the area of this guy right here, area equals 1/2 times 1/2 is 1/4 h squared. So now we're able to do the same thing as we did before. I'm not going to redraw that graph because we've done it many times already. So volume equals the integral from 0 to 5 of this thing right here, 1/4 h. H is x plus 1 squared dx. Kick the 1/4 out, square this out, integrate the pieces, put in 5, plug in 0, subtract, multiply by 1/4, bam, you're all done. And again, the hard work, and even I got a little lost in for just a moment. Man, I cannot negotiate this screen here. The area expression is 1/4 h squared. So that's really the difficulty here, right? This is the difficulty. This is the easy part. And in fact, like I said this morning, I really think this is actually easier than doing the volumes of revolution, whether it be around about the x or about the y axis, shells, or discs / washers, because all we need to know is what's the area, and we've set up the area expression. We don't need to worry about, well, where's the radius and whatever. So there it is. So these are volumes of known cross sections, and we did a whole bunch. So you're only going to have 2 for your assignment and 2 or 3 shell problems, and that is it. I'm also going to post a practice test, which is really just going to be a practice set of problems out of your book, but your final exam will look a lot like that. So anyway, I will post this up tonight. This is Monday night, by the way. And yeah, I will see y'all. Well, I'm sure I'll see you tomorrow a little bit, but see you in class on Wednesday. Have a good night.